Hello. In the journal Science on the 16th of September 2010, researchers announced a development that takes us one step closer to a computing revolution. The development of a quantum computer able to compute problems that even the fastest modern supercomputers would find impossible. Jonathan Matthews, a PhD student at Bristol University, described their development to me, but first I spoke to Professor Jeremy O'Brien, Director of the Centre for Quantum Photonics, to find out why quantum computing has such appeal.
People have been trying to develop a quantum computer for at least a decade in a serious way, and for a couple of decades people have known that such a device could be incredibly powerful for computation for particular tasks. And so there's been a big worldwide effort to realise a quantum computer. Even at this stage, it's anticipated to be decades away. And the reason for that is that you need to be able to control single quantum systems. So that could mean single particles of light, single photons, or single electrons, or single atoms. You need to be able to couple them together in complex ways to control them and manipulate them and read out the state that they're in. So it's an incredible quantum engineering challenge, if you like, to be able to make such a device.
So rather than an evolution of the existing computer, we're looking at a revolution of the sorts of technology we use.
That's exactly right. So it's a completely different way of doing computation, and the idea is to harness uniquely quantum mechanical effects. So quantum mechanics is the theory that explains how the world works at its most fundamental level, how single photons, single atoms, single molecules and so on behave and interact with one another. And it's surprisingly different to the way the world works in our everyday experience. For example, it tells us that an object can be in two places, or more places indeed, simultaneously, that two objects can be inextricably linked with one another no matter how far apart they are, such that a measurement on one will instantaneously affect the other one. And we call these effects superposition and entanglement, but that's essentially what they are. We obviously don't see that in our everyday lives. We don't see an apple that's on one side of the table and the other simultaneously. We don't see these incredible links between objects. But we do when we go to the micro scale, when we start looking at single quantum systems, and we typically need to get very small and very cold to see these effects. And the idea of a quantum computer is to harness these effects to do something useful. So more generally, the idea of quantum technologies is to use these effects to enhance information, communication and processing technology. And for a quantum computer in particular, there's tasks that we know that we can do with a quantum computer exponentially faster than we can do with a conventional computer. So that means we can do problems that are intractable on a conventional computer, and they're ones whose time taken to do the computation grows exponentially with the problem size. So if we make the problem just a little bit bigger, then it might take twice as long to solve. So say we have a problem that has 10 elements in it, and it takes an hour for some computer to solve. Well, we add one element, so we've got 11 elements, and suddenly it takes twice as long. It takes 2 hours. Whereas for a quantum computer, we don't have that. They're linked in a sensible way with one another, the size of the problem and the time taken.
You say we're still decades away from a quantum computer, but are there already devices that take advantage of quantum physics available on the market?
Yes, so two things to say there. One is that, yes, there are devices available, and second is that the work that we're reporting today hopefully brings us more like into the 5-year timescale to realise a device that can do something that a conventional computer can't do. So just to go back to the first point, there are several companies around the world who will sell you a quantum communication system which relies on encoding information in single photons, single particles of light, and communicating between two parties such that any adversary trying to eavesdrop on that communication can be guaranteed to be detected, because any information that eavesdropper gains by measuring the communication, measuring the photons that are being communicated, necessarily disturbs the state of those photons, and that disturbance can be detected by the two legitimate parties attempting to communicate. And so when they detect the presence of an eavesdropper, they know that their communication has been compromised and they abandon it and start again. So perhaps I can get back on to what we've done here. We've taken a different approach to quantum computation, where we're using so-called quantum walks to do quantum computation. And the idea here is that we do a more direct simulation of the interesting quantum system that we're trying to do a calculation with. So whether it's some light harvesting complex for photosynthesis or some molecule or material that we'd like to simulate, the idea is to do a direct simulation of that rather than to program up a universal quantum computer, which is the sort of quantum analog of the conventional computer. It's a specialized device just designed for simulating systems.
So rather than, as we have at the moment, a motherboard, a processor that can do as many calculations as we happen to need, this is a very specific device built to do essentially this one calculation.
Yeah, it's a specific device designed to do one class of computation or one type of computation, if you like. So what we would imagine doing is having an array of waveguides where we can change the coupling between them using electrodes above the waveguides, and that would allow us to reconfigure exactly what the device was doing. So it's programmable in the sense that you can dial up these couplings and do something different from run to run, but it's not universally reprogrammable. So it's not a universal quantum computer in the sense that, a PC is a universal conventional computer that we can essentially get it to do any task that we want.
Jonathan, if I could bring you in here, what physically is this device that you've developed?
This device is an integrated optical chip. It uses what we call waveguides to guide light through a monolithic structure, through a fixed structure. And these waveguides work very much like optical fibers, like pipes for light, if you will. And what we do is we pattern several of these waveguides close together so that the photons can actually tunnel directly between neighboring waveguides or neighboring pipes. And this allows us to see these superposition patterns that we call quantum walks.
What is a quantum walk, and how would it differ from a classical walk?
Perhaps I can start with a classical walk. A classical walk you can realize by dropping a marble and giving it a series of choices by going left or right as it hits a bunch of pins arranged in a grid pattern. And this will give you a normal distribution at the bottom, a bell curve. So that's based on the marble being given a choice of going left or right based on probability. But if you give the marble the possibility of going left and right, it has the possibility of interfering with itself, and you get, at the end, a very different statistical outcome. These statistical outcomes include features such as propagating much faster. The distribution propagates much quicker than in the classical case. And it's this kind of behavior that can be really harnessed in quantum technologies.
So a quantum object will give you a very different likelihood of landing in any particular place from this walk, and that's when you put one photon through. Your work is working on putting more than one through to see how that works out. What's the advantage of doing that?
In previous demonstrations, people have seen single particle quantum walks before, and it's very interesting behavior, and it's demonstrating what we call the superposition principle, which we just talked about, where you can take one particle and it can go in multiple directions at the same time. There's another very uniquely quantum mechanical property, which is called quantum entanglement, and this is where you can take two quantum systems and you can link them together inextricably. So you separate them and they're correlated, so if you do some operation on one, it instantaneously affects the other. And what we've done is to take two photons and inject them into our device, and they quantum interfere with each other in such a way that they come out of the device in an entangled state. So really what's different from the single particle case is we now have, as well as superposition, we also have entanglement between two different things.
So rather than dropping two marbles, and if we go back to the classical issue, the likelihood of them landing in any place is exactly the same for each marble. Whereas, because these objects quantumly interfere with each other, that actually changes the probability altogether of what you may get at the end of your walk.
That's exactly right. A key thing is you need the two photons to be exactly the same in every single property, but they quantum interfere with each other, and the fact that there are two photons gives you a different statistical output that if you put in one photon and then put another photon in and compare the two results.
So in terms of quantum computing, why is this an advantage?
Well, this allows us to simulate more complicated structures. So quantum walks move around an environment that mathematicians call graphs. And these environments essentially become exponentially more complicated as you linearly increase the number of photons. So if I have one photon, it's moving through a system of, let's say, 20 waveguides, then my system is of size 20. Whereas if I stick 2 photons into the device, if I inject 2 photons into the device, then I'm simulating a structure that's of the order 20 squared. And if I put one more photon in, then it's 20 squared times 20 again. And you can see where this is going. You get an exponential increase in complexity.
And this allows you to do far more calculations than would ever be possible with a traditional computer.
This allows you to move towards simulating more complicated circuits, more complicated systems than you can do with current computers, yes.
So, Jeremy, coming back to you, what do we hope to use these quantum computers for?
So these particular types of quantum computers based on quantum walks are in principle able to realise a universal quantum computer. So there's an exciting and important theoretical result to show that quantum walks are able to perform any sort of quantum computation. But in the nearer term, we expect to be able to simulate important quantum systems using these quantum walks in a sort of direct way. So in contrast to the way we do a simulation on a conventional computer where we program up the simulation and, for example, we might be trying to work out how a car goes around a racetrack. Well, there's no real one-to-one mapping between that car on the racetrack and the physical reality of what's going on in the computer. And we can do simulations on a universal quantum computer in the same way, where we program it up into some algorithm and we run it and so on. But the idea of doing a direct simulation with quantum walks is that you can sort of do a one-to-one mapping, or that you can actually see that you've got one physical system and another physical system, and you can see where the parallels between the two are. And that's sort of efficient way to do this type of simulation. And so the types of things that we might be interested in simulating are complex molecules that might be relevant to designing new pharmaceuticals or new materials. And it turns out that if we have a molecule with of order 30 atoms in it, that's the limit of what we can reliably calculate on a conventional computer, even using a supercomputer today. And the reason is that the description of that system, it grows exponentially in the same way that Jonathan described the exponential growth of the quantum walk as we add more particles to it. And that gives you a sense of how this can be used, because the complexity of the quantum walk scales with the complexity of the system. So they're both getting exponentially more complicated, and so the simulation is able to keep up with the reality, if you like. And so there's a hope that we can really do these sorts of things efficiently. Other applications include understanding natural processes like photosynthesis, which rely on quantum coherent effects for their operation. And at the moment we make solar cells using the same sort of semiconductor materials, typically silicon, that we use to make computer chips. But we know that nature does a very good job of this already. And if we could understand in detail how photosynthesis works via simulating it with a quantum walk, we might be able to design even more efficient photosynthesis type operations. There's no guarantee that nature's struck upon the most efficient means of doing things, and I think the applications of that are obvious.
So by how much do you think your work has brought forward the reality of quantum computing?
So I think it's fair to say that the majority of people working in the field of quantum information science and quantum computing specifically believe that a universal quantum computer is decades away. But we're optimistic that using this quantum walk type technique, we'll be able to make a device that's able to do things that can't be done on a conventional computer within a 5-year timescale.
Jeremy O'Brien, Director of the Centre for Quantum Photonics, and before him Jonathan Matthews, explaining how, by taking advantage of quantum walk, their system is able to model things of incredible complexity. Their paper was published in the journal Science on the 16th of September 2010. I'm Ben Valsler from The Naked Scientists, and for more science news, interviews and experiments, join us online at thenakedscientists.com.